Imagine taking the most successful laws of physics, like the equations that can perfectly land a rover on a crater on Mars.
Right, the really massive, predictable stuff.
Yeah, exactly. And then you take the equations that power, every single microscopic microchip on Earth,
Yeah.
and you put them in the same room. You would totally expect them to shake hands.
I mean, they describe the exact same universe after all. You'd think they'd get along.
But they don't. Instead, they violently try to destroy each other. Like, if you try to use our two greatest scientific triumphs at the exact same time, say, by zooming into the crushed center of a black hole, the math literally spits out infinity. It just completely breaks down.
It really is the ultimate standoff in modern science. You've got general relativity, which maps the sprawling, heavy cosmos,
Yeah.
and then quantum mechanics, which rules the microscopic, jittery world of particles.
And both are incredibly accurate, right?
Oh, absolutely. They both possess just mind-bending precision in their own domains, but under the most extreme conditions imaginable, like the literal dawn of time, the Big Bang, they absolutely refuse to speak to each other.
And resolving that standoff is the mission of this deep dive. I'm your host, and today we are exploring whether a deeper underlying framework could finally unite matter, forces, gravity, space, and time into, like, one coherent picture.
And I'll be your guide through the science side of things. It's a heavy topic, but a really fascinating one.
Definitely. Now, a quick note for you listening. This is an independent COSMORA HQ audio podcast. We're exploring the principal ideas of a highly influential theoretical framework, drawing specifically on an educational companion to the book The Elegant Universe by Brian Greene.
Right, and just to be clear, this isn't an audiobook or a substitute for the original work, but rather, our own deep exploration of the concepts it brings to light.
Exactly. So before we start bending our minds around extra dimensions and vibrating strings, we really have to establish the golden rule for this journey.
Yeah, this is crucial. We must constantly distinguish a mathematical model from physical reality. Think of a globe sitting on a desk.
Okay.
It perfectly encodes real relationships about the Earth's geography, right? But it is not the actual Earth. In physics, our equations encode relationships. Their ultimate success is judged by coherence and, importantly, experiment.
Right, so elegance on a chalkboard is not the same as a confirmed measurement in a lab.
Exactly. We have to keep our questions proportional to the evidence.
Okay, let's unpack this. To understand why these two heavyweights of physics are throwing punches at each other, we can't just skip to the fight. We need to look at how they were built. Let's start with Einstein.
The perfect place to start.
Before him, space was basically just an empty box, and time was this universal clock ticking away for everyone. Why did Einstein have to ruin that comforting, absolute view of reality?
Well, he broke it because of a strict, unyielding demand of the universe. The speed of light in a vacuum is constant for all observers, no matter how fast they are moving.
Which is so counterintuitive. Like, if I'm flying in a rocket at half the speed of light, and I shine a flashlight forward.
You'd think the beam travels at 1.5 times the speed of light, right?
Right, because I'm already moving.
But it doesn't. It still travels at exactly the speed of light relative to you. But if that speed is a universal speed limit that literally cannot be broken, something else in the equation of reality has to give.
So, by protecting the speed of light, Einstein basically forced space and time to become flexible.
Yes. That means distance and time aren't universal at all. This is special relativity. If you are moving rapidly, your clock literally ticks slower relative to someone standing still.
Time dilation.
Exactly. And the length of your rocket actually compresses. Two events that look perfectly simultaneous to you might happen at completely different times for someone zooming past you.
And these aren't just optical illusions, right? Or tricks of the eye.
No, not at all. They are structural requirements of the universe, locked in by the constant speed of light, and that was just his first major breakthrough.
Right, because a decade later, Einstein expanded this into general relativity, completely redefining gravity.
Yeah, he realized that space and time are actually woven together into a single fabric space-time. Gravity isn't some invisible tether reaching out across empty space to, pull planets around.
It's more like a trampoline, right?
Yeah, exactly. Massive objects like stars warp and curve the fabric of space-time itself. The planets are simply following the straightest possible paths, which physicists call geodesics, through that curved geometry.
And the genius of that is how he connected geometry to the actual physical feeling of weight, like the equivalence principle.
Right.
If you're standing in an elevator in deep space and it accelerates upward at 9.8 meters per second squared, You would feel your feet pressed against the floor exactly the same way you do sitting in a chair on Earth.
Which means local acceleration mimics gravity perfectly. This proved that gravity is basically just the geometry of spacetime. It gave us the concept of black holes, light bending around galaxies, gravitational waves. It's brilliant.
But then we zoom in. We leave the sprawling cosmos and hit the atomic scale, and Einstein's smooth geometric fabric just completely falls apart.
It falls apart because the microscopic world plays by entirely different rules. Down at the quantum level, the universe abandons definite classical histories.
Meaning things aren't just in one place doing one thing.
Exactly. We enter a reality governed by probabilities, amplitudes, and inherent uncertainty. Particles exhibit wave-like behavior, and fundamental forces are mediated by the exchange of other discrete particles within quantum fields.
And we should clarify the uncertainty principle here because it's deeply misunderstood. People think it's just about us having clumsy measurement tools, right?
Yeah, they think, oh, we just need a better microscope. But no, it's a fundamental blurriness built into nature. You physically cannot know a particle's exact position and exact momentum at the same time.
So the more you pin down where an electron is, the wilder and more erratic its speed and direction become. The microscopic world is inherently jittery.
Very jittery.
So how does that jitter cause the crash? Like, why can't we just apply this quantum math to gravity and get a neat little quantum gravity theory?
Well, the crash happens because of what the math requires versus what the universe actually provides. General relativity requires space-time to be a smooth, gently curving trampoline. But quantum mechanics says that if you zoom in close enough down to the unimaginably small Planck scale, that inherent uncertainty creates violent, chaotic energy fluctuations.
So the smooth trampoline becomes a boiling, frothing ocean.
Yes. And if you try to calculate how a gravitational field behaves in that boiling ocean using the standard quantum method, which, by the way, treats particles as zero-dimensional, infinitely small dots, the math literally blows up.
Because all that chaotic energy is being crammed into a mathematical point that has literally zero volume.
Exactly. The equations just spit out infinity as an answer. And in physics, getting infinity is usually a glaring sign that your theory is broken.
Right. But wait, don't other quantum theories like electromagnetism also have infinities?
They do. But physicists developed clever mathematical techniques called renormalization to absorb those infinities into a few measured parameters. But point particle gravity is unrenormalizable. The infinities just cannot be swept under the rug. The microscopic violence tears the macroscopic geometry apart.
Okay, so if the zero-dimensional dot is the thing causing the mathematical explosion when gravity is introduced, the logical next step is to, well, change the geometry of the fundamental ingredient.
Right, stop using dots. Which brings us to the theoretical framework of string theory.
So instead of treating particles as dimensionless points, string theory proposes they are tiny, one-dimensional extended loops or filaments of energy.
Exactly. As a standard point particle moves through time, it traces a single line, a world line. But a string is one-dimensional, so as it moves through time, it traces a two-dimensional sheet called a world sheet.
Which fundamentally changes how they interact. Like, 2 points colliding happens at one infinitely sharp, exact location in spacetime. Boom, infinity.
Right, but when two world sheets interact, that moment of collision is smeared out over a small region of spacetime.
That slight smearing kind of tames the wild, high-energy quantum behavior that was breaking the math, doesn't it?
It does, and that shift in geometry introduces incredible properties. Think about the fundamental particles we observe: electrons, quarks, neutrinos. In the standard model, they are just assumed to be fundamentally different entities.
But in string theory, they are all the exact same kind of string. What makes them appear different to our instruments is simply how they vibrate.
Yes.
Here's where it gets really interesting, though, because usually people use a guitar string analogy here. Pluck it one way, you get an A note. Pluck it another way, you get a C note.
That's a very common analogy, yeah.
So one string vibration gives you the mass of a quark, another gives you the spin of an electron. But, and here's where I want you to clarify its limits. A physical guitar string is made of atoms. What is a fundamental string made of? It can't be made of anything smaller, right?
What's fascinating here is that crucial distinction. We are not talking about material like nylon or steel vibrating in the breeze. These strings aren't made of anything. They are the absolute foundational ingredient.
So they're just pure energy.
Essentially, yes. We are talking about pure quantum excitations, mathematical patterns of energy that manifest in our low-energy world as mass, spin, and force charges.
And this leads to what I think is the most jaw-dropping mathematical miracle in this entire framework.
Wow, the graviton.
Yes, if you calculate the vibrational patterns of an open string one with two loose ends, you get matter particles. But what happens if you take that string and fuse the ends together into a closed loop?
Right, it has no endpoints anymore.
And when you calculate the required vibrations for that closed loop, the math literally spits out a particle with zero mass and 2 units of quantum spin.
Which exactly matches the theoretical profile of the graviton, the hypothetical particle responsible for carrying the gravitational force. This really cannot be overstated. In most quantum theories, you have to force gravity in by hand. It's clunky.
But in string theory, gravity isn't an option. The closed loop demands a graviton.
Exactly. The framework inherently contains quantum gravity. It's not a patch, it's built in.
It's an incredible theoretical victory. But, we also have to be honest about the historical timeline here. The physicists working on this in the 1970s and 80s hit some massive walls.
Oh, yeah. The early math had fatal bugs.
Like predicting particles that travel faster than light, right?
Yes, tachyons. And worse, the original bosonic string theory only described force particles. It didn't have any room for fermions.
And fermions are the actual particles that make up the matter in your body, so that's a pretty big problem.
A huge problem. So to fix those massive inconsistencies, physicists had to introduce a profound theoretical upgrade called supersymmetry.
Okay, so what is supersymmetry?
Supersymmetry is a proposed mathematical relationship that essentially bridges the gap between matter particles and force particles. It pairs them up into a single, unified family.
So fermions and bosons become part of the same framework.
Exactly. When they applied this mathematical transformation, it cured the inconsistencies, removed the faster-than-light tachyons, and gave birth to superstring theories.
I have a major problem with this, though. If supersymmetry mathematically demands that every single known particle has a heavier shadow partner, a superelectron, a superquark, where are they?
That is the big question.
I mean, we've built giant 27-kilometer-long underground tunnels in Switzerland to smash particles together at near-light speed. We've meticulously mapped the standard model. We haven't found a single supersymmetric partner. Doesn't that lack of evidence kill the theory?
It definitely strains it, but it doesn't kill it outright. The working hypothesis among many theorists is that supersymmetry is basically broken at everyday low energies.
Meaning what, exactly?
Meaning, these partner particles might be so heavy that they only pop into existence at energy levels far beyond what the Large Hadron Collider can currently reach. But going back to our golden rule, we have to be careful. Supersymmetry might just be an incredibly powerful mathematical tool for balancing equations, but completely absent from physical reality. Nature is not obligated to use the math we find elegant.
That's a great point. And as if a whole invisible universe of shadow particles wasn't enough, fixing the math demanded something even wilder, extra dimensions.
Yes, the math gets very demanding here.
We are used to living in 4 dimensions, up, down, left, right, forward, backward, and time. But the equations of superstring theory absolutely refuse to work in 4 dimensions, right?
Right. They require more space. They require extra spatial dimensions to remain mathematically consistent. Without them, you get negative probabilities, which is physical nonsense.
But since we clearly don't see extra dimensions when we walk down the street, theorists propose that these extra dimensions are compactified.
Yes, they are curled up into shapes so microscopically tiny that we pass right through them without noticing.
The classic way to visualize this is looking at a garden hose from far away. From a distance, it just looks like a one-dimensional line.
Right, you just see its length.
But if you walk up to it with a magnifying glass, you see the hose actually has a circular 2-dimensional cross-section. An ant could walk around the circumference.
It's a great analogy.
The extra dimension was always there, you just had to zoom in. But, and here's where I want to push back, that just explains how a dimension could be hidden. It doesn't explain what these hidden dimensions actually do. Where does the hose analogy fail?
Well, it fails because the hidden dimensions are not simple, smooth circles. The math often points to incredibly complex, twisted, multi-dimensional structures known as globular spaces. The hose analogy only illustrates scale-dependent visibility, not the actual intricate geometry.
Okay, so think of a French horn. The physical, twisted shape of the brass tubes strictly determines what notes can bounce around inside and come out of the bell.
Exactly. In string theory, the twisted shape of these hidden Calabi-Yau dimensions acts like the brass tubes. The geometry of the hidden space dictates exactly how the fundamental strings inside them are allowed to vibrate.
And because those vibrations determine the mass and charge of particles, the intricate microscopic geometry of the universe is literally what dictates the physical properties of everything we interact with in our vast four-dimensional world.
That is exactly it. Geometry dictates physics.
That is beautiful. But of course, physics is never that easy. By the mid-1990s, theoretical physics was suffering from too much of a good thing. They hadn't just found one consistent superstring theory, they had found 5 distinct mathematical formulations.
Yeah, it sparked a bit of a crisis. How can you have 5 different theories of everything? It makes no sense.
Right, but this led to the second superstring revolution, didn't it?
It did. If we connect this to the bigger picture, physicists discovered profound mathematical translations called dualities. They realized that these 5 apparently different theories were actually describing the exact same underlying physics, just looked at from different mathematical perspectives.
Can you give an example of that?
Sure. For example, a theory calculated with a strong quantum coupling turned out to be completely mathematically equivalent to a different string theory calculated with weak coupling. They were essentially 2 sides of the same coin.
The duality that absolutely breaks my brain is the spatial one, though. You're saying if I do the incredibly complex string math assuming a microscopic curled-up hidden dimension, and you do the math assuming a giant, sprawling hidden dimension, we arrive at the exact same physical reality.
The math works out exactly the same.
How is that possible? Doesn't that imply our fundamental concept of distance, the difference between large and small?
Yeah.
Just an illusion.
It strongly suggests exactly that. It implies that space-time, at least in the form familiar to human experience, may not be a fundamental ingredient of reality. Yeah. The variables that we interpret as geometry in one theory emerge from totally different, non-geometric variables in a dual theory.
And all these dualities eventually pointed to a single overarching structure uniting the 5 theories, which theorists named M-theory.
Right, M-theory. And M-theory demanded 11 dimensions, but it also expanded the cast of characters. We aren't just talking about 1D strings anymore.
Right, we have brains.
Yes, M-theory includes extended objects with more dimensions, collectively called p-branes. You can have a 2-dimensional membrane or branes with 3, 4, or more dimensions. Crucially, the math introduced D-branes, which are essentially multidimensional surfaces where the endpoints of open strings can attach themselves.
So look around the room you're in right now. Everything you see, the light hitting your eyes, the atoms making up the chair you're sitting on, it might all be permanently glued to a 3-dimensional brain floating in a massive, invisible, multidimensional space.
That is the brain world scenario.
The open strings that make up matter and light have their ends stuck to our brain. They literally can't leave. But earlier, we established that gravitons are closed loops of string. They have no endpoints to get stuck.
Exactly. Because gravitons are closed loops, they can leak off our 3-dimensional brain and travel out into the higher dimensional bulk.
Which would explain so much.
It does. This model-dependent scenario provides a fascinating explanation for a major mystery in physics. Why gravity is so incredibly weak compared to the other forces. I mean, a tiny fridge magnet can overpower the gravitational pull of the entire Earth.
So string theory suggests gravity feels weak because its strength is diluted, leaking into hidden dimensions that light and matter simply cannot access.
Exactly. It's a very elegant explanation.
But physics isn't just about elegance. It demands proof. To see if any of this theoretical framework actually works, it must be applied to the most extreme arenas in the universe.
The ultimate test labs. Black holes and the Big Bang.
Let's start with black holes.
Black holes are perfect because they require both general relativity and quantum mechanics to fully understand. We've known for decades, through black hole thermodynamics, that a black hole has entropy, which is basically a measure of hidden microscopic information.
Right.
And that entropy is proportional to the surface area of its event horizon. But general relativity couldn't explain what those hidden microscopic parts actually were.
And this is where string theory scored one of its most rigorous victories, right? For certain highly symmetric black holes, physicists used the math of strings and branes to count the exact number of underlying quantum states.
Yes, and the microscopic calculation perfectly matched the macroscopic entropy expected by thermodynamics. It was a huge triumph of internal consistency.
And doesn't it also deeply inform the famous black hole information paradox? Like, when something falls into a black hole, is that information permanently destroyed?
Yes, through something called gauge-gravity duality, string theory provides a compelling answer.
Think of a hologram. A flat, 2-dimensional piece of plastic that holds all the visual information of a 3-dimensional image. Are you saying black holes work like a hologram? The information of everything that falls in isn't lost, it's just perfectly preserved on the two-dimensional surface of the event horizon.
That is the essence of it, yeah. A gravitational theory in the bulk space can be mathematically equivalent to a non-gravitational quantum theory on the boundary. This strongly favors unitary quantum evolution, meaning information is never lost. It is preserved on the boundary.
Okay, so that's black holes. But what does this all mean for the Big Bang? Does string theory actually prove cosmic inflation? Because a rapid expansion of high-energy quantum fluctuations sounds like the exact place you'd want to use string math.
We have to tread very carefully here. String theory provides candidate mechanisms for inflation, perhaps involving the energy fields of how those extra dimensions curl up, or the energy released when massive branes collide in the bulk.
But does it confirm?
No, it is highly model dependent. There is no single uniquely established string inflation scenario that matches our cosmological data perfectly.
Which leads to what critics call the vacuum selection problem. If you have 11 dimensions, there are an unimaginable number of ways to fold up the extra one.
Right, the string landscape.
Yeah, and each different geometry produces a universe with completely different particles and forces. And sometimes physicists use the anthropic principle to explain it, saying, well, of course we see the exact geometry that produces our specific universe, because if it were any different, we wouldn't be here to observe it.
It's a controversial take.
I have to be honest, that feels like a massive theoretical cop-out. It doesn't actually predict anything.
You are echoing a major criticism within the physics community. Anthropic reasoning is a highly debated strategy. It highlights the vast possibilities of the string landscape, but without a fundamental mechanism that dictates why our specific vacuum was selected out of, 10 to the 500th power possibilities, the predictive power of the framework is severely challenged.
So this brings us to the ultimate question. If we can't build a particle accelerator the size of the Milky Way to directly see a Planck-length string, how can we ever know if this isn't just beautiful math? What indirect clues are we desperately looking for?
Well, we look for anomalies. We search the LHC data for those heavy supersymmetric partner particles we talked about.
Okay.
We look for Kaluza-Klein states, which would appear as heavy echoes of standard particles resonating within the hidden dimensions. We look for missing energy in collider collisions that might indicate a graviton has escaped into the bulk.
Have we tried testing gravity itself?
We have. We test gravity at microscopic submillimeter distances to see if the standard inverse square law suddenly changes due to extra dimensions.
But so far the results are deafeningly silent, right? The colliders haven't found a single shadow particle or dimensional echo.
Nothing yet.
And our gravitational wave observatories. They are detecting ripples from colliding black holes billions of light years away. But the signals perfectly match the equations Einstein wrote down a century ago.
Which forces us to make a critical distinction between a mathematically fertile framework and an empirically confirmed scientific theory. String theory has immense explanatory power. It unifies forces, tames infinities, and gives profound insights into black hole microstates.
But internal consistency is not the same as experimental proof.
Exactly. We cannot confuse an attractive possibility for a measurement.
It's the difference between drawing a flawless, mathematically perfect map of an uncharted continent and actually sailing a ship there to prove the dirt exists.
That's a great way to put it.
So, as we wrap up this deep dive, where does this monumental effort leave us?
It leaves us with a permanently altered understanding of physics. Even if a unique realization of string theory in nature remains unconfirmed, the quest to unite gravity and quantum mechanics has pushed mathematics to completely new frontiers. More importantly, it has forced physics to rigorously question what counts as fundamental.
It really forces us to ask if the things we take for granted, particles, space and time, or the true building blocks, or just the shadows of a deeper machinery. We've covered a massive amount of conceptual ground today, but to truly grasp the historical narrative, the brilliant thought experiments, and the full weight of these arguments, I highly encourage you to access Brian Greene's complete original book, The Elegant Universe, Superstrings, Hidden Dimensions, and the Quest for the Ultimate Theory.
It's a fantastic read.
It really is. You can find it legally in print as an ebook at your local library or through an authorized audio service.
And as a final provocative thought for you to mull over, think back to those spatial dualities we discussed earlier. The mathematical proof that a universe with a microscopic hidden dimension can be completely identical to a universe with a gigantic one.
Right, the idea that distance might just be a matter of perspective.
Take that to its logical conclusion. If geometry itself can be swapped out like a mathematical variable, what if space and time aren't the fundamental canvas of the universe at all? What if the vast three-dimensional stage we walk on every single day is not an absolute reality, but simply the large-scale collective mirage of a deeper, completely spaceless quantum reality?
Wow. That is a thought that will keep you staring up at the night sky for a long time. Thanks for taking the dive with us.